Hi, my name is Michael Teng, and I'll be presenting semi-supervised sequential generative modeling. This is work done with Tuan, Adam Scibior, and Frank Wood. So we want to see if we can extend semi-supervised learning and generative modeling techniques to time series data. And as an example, say we have trajectory of driving, and in addition to modeling that, we want to be able to infer, am I going straight or am I turning, over some sequence of observations. We're going to be operating in the variational autoencoder family, which uses neural nets to parameterize a joint distribution over observed x and latent z's, as well as the variational distribution z given x. And these two objects are joined jointly using the evidence lower bound, or a tighter version, the importance weighted autoencoder. And then when you finish training, you use the Q object that you trained to do variational inference. The semi-supervised VE is only different in that, in addition to the latent z's, you have another discrete latent variable y, which you sometimes have a known label for. So when you have paired xs and ys, you use the supervised elbow written above, and an additional classifier term during training. Whereas if you don't have any, you just use the regular unsupervised elbow. This is known as the M1 plus M2 method. And here we just list some examples or applications of sequential data and the corresponding hard inference task that you might want to perform in these applications. So what we propose is the semi-supervised VRNN, and a VRNN, for those unfamiliar, is simply a VAE at each time step, parameterized by the hidden state of an RNN at that time step. And so you have your random variables, x, y, and z, and then you feed them back into the RNN every time. And this is what captures the temporal dependence of the model. The inference network here works very much the same, and they share a RNN architecture, in fact. So we can write the elbow for this sequential model below. And as you can see, there's no problem to do model learning, which is training the theta parameters using this sequential elbow. Whenever you don't have y's or z's, you sample, and then that provides a lower bound to the evidence over x and known y's. So our contribution then is to say, let's look at the original M1 plus M2 method for static models. We notice that in addition to the two elbow terms, we have this additional classifier term, which is there because you are otherwise not using the paired x's and y's in your training objective in any way to encourage the inference network to move closer to inferring the correct y given x. And there's just no training signal in the elbows for the paired data. So you have to include this additional classifier loss. And that is usually controlled with a optional hyperparameter alpha, which just says, here's how much we trust these supervision terms. While this can be extended to the sequential domain, there are some problems because in each sequential example, you have a varying number of supervised terms. So in the static case, you can always artificially balance your mini batch by saying, I'm going to have always 10% supervision in each mini batch. But it's hard to do that in time series data because even in a single mini batch example, you might have half supervision across like n time steps. And then in a different example, you might have less than 1% supervision. And while we can extend the M1 plus M2 loss using either reinforce for the discrete lane variables or using wake sleep for the discrete lane variables, you always will have an additional classifier term written in blue, and as the first term in the final equation in semi-supervised wake sleep. And so we want to get rid of these two separate terms by unifying them into basically one single loss objective. And we do this by introducing caffeinated wake sleep, which is saying, let's just do regular reweighted wake sleep, assuming everything is unsupervised. Except when we sample Ys, if we do actually have the supervised term or the supervised label, let's just replace the sample that we got with the actual known label. And in doing so, we can have one single unified loss and something that is viewed as teacher forcing wake phi. In both caffeinated wake sleep and semi-supervised wake sleep, you learn model parameters using the sequential elbow, as I mentioned. Looking at the results, we see that for MNIST, we get higher validation accuracy as well as good generative samples using CWS. In handwriting, we are doing a very hard inference task where we're trying to model the XY pen coordinates while trying to infer what character is being written. And this is hard because it is a 70 class discrete categorical in the latents. And we see that the M1 plus M2 method using reinforce just does not do well. And then we have an additional baseline denoted as iWay in the top left, which is let's train with 12% of the entire data set and see how that compares with semi-supervising with 12% supervision. And then we have conditional generation in blue as from an RNN from previous work, as well as from our model in the bottom, where it's actually trying to conditionally generate the text written. In this fly example, we are showcasing that caffeinated wake sleep is the only method that works when you have very sparse supervision. And in this data set, it's less than 10%. And the other methods simply do not train stably. We're trying to model fly trajectories and the high-level actions that happen when these two flies sometimes interact. Here is some future work and acknowledgements for each of the authors. Thank you.